Future Pragya Sahu, PMRF scholar at Department of Chemistry, IT. So in last class we have studied this case law. After that we were studying the application of the case law, in which what we studied that if it is difficult for some of the reactions to calculate the enthalpy change. Okay, so in that case what we can do, we can calculate them using the case law, which states that the enthalpy change for a reaction is same whether it goes via a single state or multiple state. Okay, providing that the initial and your final state is same. Okay, so in that case your enthalpy change will be same. Okay, so this was the this statement. Now let us study what is the lattice energy. So the lattice energy is defined as the amount of energy required to completely remove the constituent ions from its crystal lattice to an infinite distance. So if you are removing ions, okay, so we are removing constituent ions from a crystal lattice, okay, and what we are doing, we are moving these ions to an infinite distance, okay. So in order to remove these constituent ions from their crystal lattice to an infinite distance, you will require energy, okay. The energy required will be called as the lattice energy. So the amount of energy which you require in order to remove the constituent ions from its crystal lattice to an infinite distance, that is called as lattice energy. And so, and we can also call it as a lattice effect. So lattice energy or lattice enthalpy. So both terms can be used. From the above equation, it is clear that 788 kilojoule of energy is required to separate Na plus and Cl minus ions from 1 mole of sodium chloride. Let me first write the equation. So the equation is pure sodium chloride, okay, forming sodium ion gas and chloride ion gas. Okay. What we are doing? We are removing the constituent ions. So ions in this case is what? Na plus and Cl minus ions. Okay. So we are removing them to an infinite distance, and if there is the energy required or the change in energy will be called as the lattice energy or lattice enthalpy, and in this case it is plus of 788 kilojoule per. So in order to remove the constituent ions, which is here in this case is uh, sodium cation and chloride anion, then the how much energy is required? That is 788 kilojoule per mole. So this energy that is required, it is called as the lattice energy, and we can also refer to it as the lattice enthalpy. So lattice energy or enthalpy. So now let us move to the next slide. Is bond Haber. So this is very important. Bond Haber cycle is an approach to analyze reaction energy. Okay? And it was named after two German scientists. First one is Max Born. Born came from Max Born, and this Haber came from this scientist Fritz Haber, and they have developed this cycle. So, and they came together and formed this Born Haber cycle in order to analyze the reaction. Okay? This cycle is concerned with the formation of an ionic compound from the reaction of metal with a halogen or other non-metallic elements such as oxygen. Okay? So the cycle is concerned with the formation of an ionic compound. We are trying to form an ionic compound from which reaction? By reacting a metal with a halogen. Okay? Or other non-metallic elements such as oxygen. So Born-Haber cycle is primarily used in calculating lattice energy. So in order to, so you can calculate lattice energy. We can calculate lattice energy using Born-Haber cycle. Using Born-Haber cycle. That cannot be measured directly. Okay, so in the earlier in the last class example, I have shown you that there are some of the energy changes which we cannot measure. Okay, so that which are difficult to measure. Okay, so in order to measure that, we are using Hess law. So here Born-Haber cycle can also be used to calculate that. Okay, that here it can be used in calculating the lattice energy that cannot be measured directly. Okay. So the Born-Haber cycle applies Hess law, okay, to calculate the lattice enthalpy. So in order to calculate the lattice enthalpy, what Born and Haber do, they applied this Hess law. For example, let us consider the formation of a simple ionic solid such as an alkali metal halide. So metal halide is what? Your metal will be there and your halide will be there. Okay? So this is what metal halide. Okay. So for the formation of an ionic solid such as metal halide, the following steps are considered. Okay. So let us write this. First, what will happen? Your metal in solid state will react with your halogen, that is in gaseous state, and one second. And what will it form? Metal halide. Okay. So if this metal reacts with the halogen, it will form metal halide. If metal halide is formed, what will it be? Metal MX. Okay. So this is what? This is the heat of formation of metal halide. Okay. So this is what? Heat of formation, that is delta HF of metal halide. Okay. This can go also via different. Let us say for this reaction to occur, this will not directly react with this. Okay. So in order to calculate that, okay. So in order to calculate that, what we will do? First, this metal will go from its solid state to gaseous state. Okay. Your metal will go from solid state to gaseous state, and what we call it? What this kind of heat change is called? Solid to gaseous. molar heat of sublimation. Okay, that was heat of sublimation. Let us say in this case it is delta H1. Okay, the enthalpy change in this process is delta H1. Now, what will happen? This metal will now from it will go from this state to metal ion. Okay, because in order to form your Mx, you will have to form M plus and X minus. Okay, so you will have to reach this state in order to form your Mx. So to form this and this, your uh, metal will have to go through this process. Okay, so what will happen if your now your metal is getting converted to its ionic state? Okay, now we have this, and what will happen with this gas? So first this will convert into the atom. Okay, then after that, let us say enthalpy change in this case is delta H. After that, what will occur? From this gas form to it will go to its anionic form. Let us say enthalpy change in this case is delta H4. Okay? Delta H4. In this case, it is delta H3. Now what will happen? You have M plus in gaseous state and X minus in gaseous state. So what will happen? They will react together. M plus in gaseous state and X minus in gaseous state. They will react together and form Mx. Okay. So if they react together, they will form this. Okay. Let us call this U, which is the lattice enthalpy for the formation of solid. So this one is what? The lattice enthalpy for the formation of Mx. Okay. What was delta H1? So let us write. This is your U. Okay. This was your U. What is your delta H1? Delta H1 is nothing but enthalpy change for the sublimation. Enthalpy change for the sublimation. And what is in this case is happening? Your metal is solid getting converted to metal to gas. Next, what is your delta H2? This one, this is enthalpy change for the dissociation of half moles of H2 to, okay, because here it was H2, now you have to dissociate it and form X8. Okay, so now after that, what was delta H3? This one, this is ionization energy. Okay, this one is your ionization energy. So this one is your ionization energy, and what is happening over here? Your M getting converted to M. What is delta H4? Delta H4 is electron affinity for the conversion of X to X minus. Electron affinity for the conversion of x to x. Okay, so in order to get x minus from x, this x will have to take an electron, and that will call as electron affinity. Okay, and U was your nothing but the lattice enthalpy for the formation of mx, and delta HF is your enthalpy change for the formation of solid mx, enthalpy change for the formation of solid mx, mx that is in solid state directly from its element. Okay, so these are the different kind of enthalpy changes that is involved in this reaction. Okay, now we clearly know what are these different kind of these things involved. Now we know the Hess law. So according to the Hess law of heat of constant summation, Hess law of constant heat summation, what will happen? So this delta H, that is from this to this, will be equal to summation of all these enthalpies. Okay, whether so here this is a single step. Okay, this is multi-step. This was single step, and it is multi-step. So delta H in case of single step will be equal to the enthalpy change in the multiple step. So enthalpy change in the multiple step will be what? Sum of all these enthalpy steps, which is delta H1 plus delta H2 plus delta H3 plus delta H4 plus U. Okay, these are all the energy changes values. Okay, so according to the Hess law, so I will write it over here that according to the Hess law of constant heat summation, what will happen? Your delta HF will be equal to delta H1 plus delta H2 plus delta H3 plus of delta H4 and plus. Okay. So here it was written that von Haber cycle applies his law to calculate the lattice. Okay. So you can easily calculate the lattice enthalpy from this reaction. Okay. So if you know all these values, you can easily calculate U. You can easily calculate U. Okay, that is lattice. Okay. So now we have studied for MX. Let us now study how to calculate the lattice enthalpy of sodium chloride using the von Haber. So let us use this von Haber cycle to determine the lattice enthalpy of the sodium chloride. Since the reaction is carried out with reactants in elemental form and products in their standard states at 1 bar, the overall enthalpy change of reaction is also the enthalpy of formation for sodium chloride. Also, the formation of sodium chloride can be considered in 5 steps. Okay. So here they are saying that since the reaction is carried out with reactants in their elemental form, okay, and the products are in their standard state, so the overall enthalpy change of the reaction In this case, what we call this enthalpy change, we call it enthalpy of formation, because what is happening, the sodium chloride is getting formed. Then what we will call it? It is enthalpy of formation of sodium chloride. Okay. So also the formation of sodium chloride can be considered in 5 steps. That is, the sum of the enthalpy changes of these steps will be equal to the enthalpy change for the overall reaction. That is your enthalpy of formation, from which the lattice enthalpy of sodium chloride can be. Okay. So this is basically that what it says, that you are forming sodium chloride from this, or from in a single step or a multiple step. Then you can easily calculate the lattice enthalpy of formation of your sodium chloride. Let us see how we can calculate. Okay. So I will erase these things. Okay. Let us write the reaction for the formation of sodium chloride from its elemental state. Okay. So what will happen? Your sodium exists in your solid form, and chlorine. Okay. So they react together and form sodium chloride solid. So what we call this? State of. So this is what enthalpy of formation of sodium chloride. Let us say this sodium from its solid state goes to sodium to its gaseous state, and the enthalpy change in this reaction is your delta, which what will be? This will be sublimation. Okay, enthalpy of sublimation, rate of sublimation. Okay. Now, in order to see what we have to form, we have to form Na plus gaseous and Cl minus gas, and they will form NaCl. Okay, so we have to get to this state. Okay, so now we have sodium gas. Now we will ionize. This will ionize to form sodium ion, and let us say this is enthalpy change in this reaction is delta H2. Now we have sodium plus ion in gaseous. Let us now see what happens to this chloride. So this chloride will first form this chlorine, here Cl2, in it will dissociate to form Cl. Okay, so let us say this is delta. Now this Cl gas will convert into Cl minus ion gas. Okay, now we have Cl minus and Na. What will happen? They will react together and will form sodium chloride gas. And what will it call? The lattice enthalpy for the formation of sodium chloride, okay, which is denoted by U in this. Okay. So your delta HF is heat of formation of sodium chloride. Sodium chloride, that is NaCl. So delta H1 is heat of sublimation. Sublimation, and your delta H1 was heat of sublimation. Delta H2 is ionization energy. Okay, so ionization energy. So here heat of sublimation of what? Sodium in solid to sodium to gaseous state, and ionization energy of sodium to sodium ion. Okay, and delta H3 is your Dissociation energy. Dissociation energy of what? Your chlorine. Dissociation of your chlorine. Cl2 to Cl. Dissociation energy. And your delta H4 is electron affinity of Cl. Electron affinity of Cl. Okay. So this is what you have: delta Hf, delta H1, delta H2, delta H3, and delta. So here U is the now U is what? Your lattice energy of NaCl. So if see, we have to calculate the lattice energy of NaCl, and these values will be given to us. Let me write these values. So I will write these values here. Delta Hf is given minus 411.3 kilojoule per mole. Similarly, delta H1 is given, that is 108.7 kilojoule. 108.7 kilojoule per mole. Delta H2 is 495.0 kilojoule per mole. Delta H3 is 244 kilojoule per mole. And your delta H4 is minus 349.0 kilojoule per mole. Okay. So now, if you know all these values from Hess law, we can easily write this. Okay. Here's the same case from Hess law. According to the Hess law, your delta Hf will be equal to delta H1 plus delta H2 plus delta H3 plus U. Okay. So this was your delta H4. So delta H4 plus U. So let us write your delta Hf will be equal to delta H1 plus delta H2 plus delta H3 plus delta H2 plus U. Okay. So we know all these values and we have to calculate. So we will just substitute these values. And this is according to the Hess law. Okay. Let us substitute these values. What we will get? Delta Hf is minus 411.3 equal to delta H1 is 108.7 plus delta H2 is 495 and delta H3 is 240 plus delta H4 is your minus of 349 plus of you calculate Q, you will get 108.7 plus 495 plus 244 plus and minus will become minus and it will become 349. And if you take this minus to this side, it will become plus of 411.3. So if you calculate this, you will get minus of U equal to 788 kilojoule per mole. Okay, so this implies that your U will become minus of 788 kilojoule per mole. That means the lattice enthalpy, that is lattice energy for NaCl, that is sodium chloride, is minus of 788.0 kilojoule per mole. So This is how you can calculate the lattice enthalpy. Now we have studied the Hayes law and how we can use the von Haber cycle in order to calculate the lattice energies and lattice enthalpies. Now let us move and study what is the second law of thermodynamics. So, what? So why there is the need for the second law? So we know that from the first law of thermodynamics, what it says that the energy of the universe is conserved. Okay? That is, the energy of the universe remains constant. Now let us consider the following processes. First one is, let us consider a glass of hot water over time loses heat energy to the surrounding and becomes cold. Okay? Let us say you have water in this glass, okay, hot water. If you leave it for some time, what will happen? Let us say you kept it for 1 hour, and after that you came and checked the temperature. Let's say for initially it was at 70 degrees Celsius, and you came after 1 hour and found out that now the temperature of this water has become 45 degrees Celsius. So what is happening here? Here there is a loss of heat energy, and from to where it is happening, that means your hot water is getting is losing its energy to the surrounding, and thus it is becoming cold. That's why its temperature is getting decreased. Now let us this end example. So when you mix hydrochloric acid with sodium hydroxide, it becomes sodium chloride. Okay, and water, we have studied this HCl plus sodium hydroxide. They react together to form sodium chloride and water. What happens? So this reaction was exothermic. Okay, and you must remember by now that what will be its value? Minus 57.32 kilojoule. Okay, here you know that it is minus 57.32 kilojoule. So the thing is here that it is minus. This is minus of 57.32 kilojoule. That means this reaction is happening with the evolution of heat. Okay, because it is negative, that means it is an exothermic reaction, which means there will be the evolution of the heat from your system. So in both of these processes, the total energy is conserved and are consistent with the first law of thermodynamics. Okay, but the reverse process, that is, if we are going from cold water to hot water. Okay, what if your cold water is becoming hot water by absorbing heat from surrounding on its own? It doesn't occur spontaneously, right? Okay, if you keep cold water, okay, and if you think it will become hot water by absorbing heat from the surrounding. Is this process spontaneous? Will this process occur spontaneously? No. So, the cold water becoming hot water by absorbing heat from the surrounding, that is the reverse process of this, doesn't occur spontaneously, even though the energy change involved in this process is also consistent with the first law. Okay. However, if the heat energy is supplied to cold water, so let us say if heat energy is getting supplied to the cold water, then it will become hot. Okay. So you are providing heat to the cold water, uh, its temperature will increase and it will become hot. Okay? That is the change that doesn't occur spontaneously and can driven by supplying energy. That means this change is not spontaneous. What we'll have to do, we will have to supply energy in order to get hot water from the cold water. Similarly, in order to get similarly, when a solution of sodium chloride doesn't absorb heat energy on its own, okay? uh, if you think that the reverse reaction, that is your sodium chloride and water forming your HCl and sodium hydroxide. That is, a solution of sodium chloride doesn't absorb heat energy on its own to form hydrochloric and acid and sodium hydroxide. But this process cannot be driven even by supplying energy. So if you think you can get back to the initial product by supplying some heat or energy, then still you can't go back to your initial state. Okay, that means your the reverse. This is irreversible. So these processes cannot be driven even by supplying energy. So from this kind of our natural experiences, we have come to know that certain processes are spontaneous while the others are not. That means here in this case it is non-spontaneous. Okay? Okay. So here in case of your cold water to hot water, it was once again I'll write it over here that from cold water to hot water is non-spontaneous. Whereas this going back to your hydrochloric acid and sodium hydroxide, that means some of these processes have a preferred direction. Okay, here they will occur only in a single direction, okay? Not in the reverse direction. So, in order to explain the feasibility of the process, we needed the second law of thermodynamics. Okay, so we don't know whether these processes will occur or not, whether this is spontaneous or non-spontaneous. So, in order to understand that, we needed this second law of thermodynamics. So, what are the various statements of the second law of thermodynamics? First one is that it uses entropy. Okay, so the second law of thermodynamics introduces another state function that is entropy. So what is entropy? So the entropy is a measure of the molecular disorder, that is a randomness of a system. Okay? Once again, my system was yes, but the entropy is a measure of molecular disorder, that is randomness of a system. But the thermodynamic definition of entropy is concerned with the change in entropy that occurs as a result of a process. Okay, so the change in entropy that occurs as a result of a process, and it is defined as ds, that is change in entropy, ds is equal to change in reversible heat. Okay, so this is dq by t. T is your temperature. Okay, so this is what is your second law of thermodynamics, where your entropy is concerned with the change in entropy that occurs as a result of a process. Okay, so entropy is nothing but a measure of the randomness of the system. What is a statement for the entropy? So, the second law of thermodynamics can be expressed in terms of entropy. The entropy of an isolated system increases during a spontaneous. So, what it says that if you are taking an isolated system, okay, and it is going under a spontaneous process, then what will happen? The entropy of the system will always increase. Okay, that means if your process is spontaneous and your system is an isolated system, then the entropy of the system will always increase. Okay, for example, if there is an irreversible process, okay, irreversible process, that is the process is very spontaneous, that is here let us take a spontaneous expansion of a gas. A gas is expanding uh, spontaneously. So in that case, what will happen? So entropy will increase. Okay, that means will be greater than zero. Okay, so it will always decrease. What is delta S total? That is your delta S of system plus delta S of surrounding. Which is your, if this is, that is your delta S of system and delta S of surrounding will be greater than delta S total is what? Your delta S universe. That means it will be greater than your delta S of system plus delta S of surrounding. Now let us study the Kelvin's Planck statement. So what is Kelvin's Planck statement? It says that it is impossible to construct a machine that absorbs heat from a hot source and then converts it completely into work by a cyclic process without transferring a part of heat to a cold. It means that, let us say, there is a system and it is absorbing heat from a hot source. Okay? Let us say this is a hot source and it absorbs some heat. Okay? Now, this heat cannot be completely converted into work by a cyclic process without transferring a part of heat to a cold state. Okay? So, this is what was the Kelvin's Planck statement. And the second law of thermodynamics is why even an ideal frictionless engine cannot convert 100% of input heat into work. You cannot convert completely heat into work. Okay, so 100% it is not possible. Okay, this is what the statement. So the even if the engine is an ideal engine or frictionless engine, it cannot convert your 100% of input, that is your heat, to 100% of output, that is your work. Okay. So Conrad, on his analysis of heat engines, found that the maximum efficiency of a heat engine which operates reversibly depends only on the two temperatures between which it is operated. Okay, so the Conrad analysis on the heat engine did the analysis, and he found that the efficiency, that is the maximum efficiency of the heat engine which is operating reversibly, it depends only on the temperature difference in between which it is getting operated. Okay. So what is efficiency? Efficiency is your work performed divided by the heat absorbed. Okay. So how much energy you are giving and by what amount it is getting converted into work, that is that we call it efficiency. So it is equal to, efficiency is denoted by eta, and it is equal to, let's say, QH amount of heat was absorbed, and then it was the work performed was QH minus QC. So what will it become? Minus of. So this is what will be the efficiency, where your QH is equal to heat absorbed from the hot reservoir. Okay. So this heat you are getting from the hot reservoir, what will QH amount of it? So what will happen? It will absorb the heat and will use this heat to do some work. So let us say QC is the heat transfer to the cold reservoir. If this is the case, and W is the work done, W is your work done. So what will happen? Your Q amount of heat is getting converted into heat transfer to the cold reservoir and the sum of the work done. So your work performed will be equal to QH minus. This is what we have written over here. That is efficiency is equal to work done divided by the heat absorbed. So you were getting W, that is QH minus QC from here, because the amount of heat absorbed will be used in doing some work, and some of the heat will be transferred to the turbine. Okay. So this is what is the expression for the. Okay. If you solve this, you will get, I'll write it over here, that theta QH by QH will become 1, and it will become QC by QH. So this is the equation. We know that for a reversible cyclic process, if the process is cyclic, what does it mean? So delta S system plus delta S of surrounding is equal to 0. If this is the case, then what will happen? So delta S system will be equal to the minus of delta S of surrounding. This is why, because this is 0 because your delta S of universe is equal to 0. This is because the okay, so this was the case where your delta S universe is 0. So if delta S universe, that is entropy change, is 0, then for a reversible cyclic process, then your delta S universe is 0. That means your delta S universe is your delta S system plus delta S surrounding. That will be 0. If that is the case, your delta S system will be equal to the minus of delta of surrounding. What is your delta S of system? From here, delta S is equal to dq by t. So what will happen? For system, it is q h by ph, and it is equal to minus of q surrounding is qc by pc, because this was the heat absorbed by the system at temperature T. Okay, so this Th is the temperature of the your hot reservoir. So this was the heat absorbed by the system. Okay, QH, and this is the entropy change. Okay, and this is transferred to the surrounding. That is QC amount of heat is transferred to the cold reservoir at temperature Tc. Okay. If you arrange this equation, what you will get? Minus of Tc upon Th equal to Qc upon Qh. So if we multiply this, okay, so it will become minus Tc by Tf equal to Qc by Qh. If this is the case, we can write it Tc by Th equal to Qc by Qh. We can write it like this. Okay, so we can write Tc by Th is equal to Qc by Qh. And if we substitute this value of Qc by Qh in this equation, here in this equation 1, what we will get? Substituting the value of Qc by Qh in equation 1, what we will get? We will get theta is equal to 1 minus Qc by Qh equals, and if you solve this, you will get 1 minus Tc by Th. Okay. Since your Th, that is the temperature of hot reservoir, is always greater than your temperature of cold reservoir, what it implies? That if Th is always greater, that means this value, there will always be some values. That means this will be always be positive value. So if this is the case, we are subtracting it from 1. So it will always be less than 1. So if this is the case, that means your efficiency will always be less than 1. That means here your temperature of cold reservoir of hot reservoir is always greater than the temperature of cold reservoir. If this is the case, your efficiency, that is eta, will always be less than 1. Eta will always be less than 1. That means efficiency will be less than, which is this statement that of the second law of thermodynamics, which states that even the the engines cannot convert 100% of input into work. Okay, if that will be the case, your efficiency would be 1. Okay, but it is not here, so your efficiency is always less than 100%. That is, it will always be less than 1. Okay, so here they have explained it. Okay, that your efficiency eta will be less than. So in order to calculate the efficiency in percentage, this equation can be expressed as eta equal to efficiency in percentage. Okay, so if we want to calculate the efficiency in percentage, this equation will become as efficiency in percentage will be equal to 1 minus Tc by Th and multiplying whole with 100. So it will become your percentage. Okay, so this is what. So it is always less than 100%. Okay, so the eta is always less than 1. So this value will always be less than 1. So it will be always less than 100. So this is what we have studied in the second law of thermodynamics. Okay, so in next class we will study the Clausius statement of the second law of thermodynamics, and then we will solve some problems. Okay, so this is what I had for this lecture, that is we studied the Born-Haber cycle. Okay, first we studied the lattice energy, then we studied how to calculate the lattice energy or enthalpy using Born-Haber cycle, and after that we came to the second law of thermodynamics, studied their need and the statements of this law, and then we studied the entropy, and after that we studied the statement, that is Kelvin Planck's statement. This is what was the Kelvin Planck statement? That is, it was impossible to construct a machine that is obsolete from a hot source and converts completely into work. Okay, so it cannot be completely converted into work. This was what the Kelvin Planck statement. Okay, next we calculated the expression for the efficiency. Okay, so this is the I'll end the session now. Okay, so in next class we will study the process.